I could have functions in each and one of the entries. What can you say about A evaluated at pi halves?
It equal 1.
Do you guys agree?
Yep.
What if A were equal to this? What do you guys think you could say about A evaluated at 1?
It equal 2 over pi.
Hold on, I misspoke, everybody. Don't listen to me. What can you say about A evaluated at pi halves?
It equal 1.
2. Brad, you see where... Oh, jeepers, I still messed up. Brad, I'm talking too fast in answering your question. I meant this to be a completely different matrix. I shouldn't call it A, I'll call it B. Can you agree that A and B are not the same matrices? A of t and B of t are different.
Yeah.
They're distinct matrix functions. But I think A of pi halves is equal to B of pi halves.
Okay.
And the author was asking, oh, he didn't choose pi halves, he chose zeros and ones. Same idea, nothing.
Okay. So if you don't have any t function in there, is it just technically right?
Good point, yes, I agree. That would be a default answer, yes.
Is it really valid to have a sign t as an entry within a matrix?
Yeah, as a matter of fact, you and I can even integrate matrices and differentiate them and take the limits of them just by component-wise integrating, differentiating, or taking limits. Yes,
Okay.
and it will be the case this semester for us.
But can you necessarily do control reduction and operations on matrices that don't have linear components?
Oh, we will. Yes, we will be reducing, whatever that means. Matrices where the entries are functions this semester. Yeah, we're solving higher order DEs. If anybody's seen that, I'm referring to the variation of parameters technique. Sir, before I answer your question, Brad, I think I've answered yours incorrectly.
Okay.
You said to answer that question, why not just put constants, one here and one there?
Yeah.
He asked you to consider distinct matrix functions.
Okay.
For which these are the same. So I think I did misguide you in the answer.
Okay.
So I think constants in there would not have answered this question.
Yeah, that's what I was going to ask.
So okay, I'm glad you comment. Yeah. What about this? What can you say about its transpose? Same thing. What do you mean it's the same thing? Where'd you get that? Oh, so you're suggesting when I take this row and use it, my new first column, the same as the first column before. When I use the second row, use my second column, same as the second column before. I think this is an interesting example where I think the transpose of the original matrix is equal to itself. If ever the transpose of matrix is equal to itself, Brad, something you bring it up from the homework, I didn't mention. We sometimes classify A as being, as you guys read last night, I hope, symmetric. Asymmetric has that quality. Why do we use the word symmetric? Piece of cake. Look at the line down the main diagonal. What you see on the other side is the same. Did you see that? What about this one? What about the transpose of what would you get? You're giving it away. You get the same as the original one, right? Oh, I made a mistake. They're out of opposites. You're right. I guess it's going to be the opposite. So from now on, if ever you have a transpose of matrix being the opposite of the original one, sometimes we say it's skew symmetric or anti-symmetric. I don't even know what the language your author uses.
Okay.
He uses both. So I'll use them interchangeably in class. If I ever do use them, it doesn't pop up that often.
Is it really important, the terminology for those? But I mean,
It's not terribly important. I do think these are interesting. Well, this will be important.
okay, well, I mean the transpose obviously, but
No, I mean symmetric matrix would be important.
oh
For
yeah,
you and
yeah.
I.
But to know like upper triangular, I mean, is that really like?
I just think it's obvious.
Yeah, I mean it just looks easy, but
You know, you guys, when it comes to conic sections, when we rotate our axes,
Yeah.
there will be one technique I give you this semester where I will be exploiting the fact that I have symmetric matrices. So
Okay.
yeah, it will become this one will become important for us. Notice with anti-symmetric, I necessarily have to have zeros down the main diagonal because they don't move, and zero is the only one number that doesn't change when you look at it as negative.
So does, in your opinion, does knowing how to do all the summation, like proof of the multiplication of matrices, is that important? Or do we just need to know how to actually go through it?
It wasn't proof, it was just a
Or
construction.
like, yeah, what it was defined.
For me, the component-wise idea of multiplication is even more important. That's the theoretical part. Yes. Can I give you an example?
Yeah.
Something else I probably missed in the homework set. Do you think this is true? I think it seems reasonable, but you know what? I can state this as a theorem. And I think this would be a good test question right here. Watch. And so if you were to prove this, any ideas?
I would convert to component-wise summation.
I would too. Matter of fact, can I say it slightly differently? How about if you and I look at an arbitrary element in these matrices? Let's see when I take a peek at an element in this matrix right here. I guess symbolically speaking, for me to identify that I'm discussing an arbitrary element in this matrix, maybe I should, I don't know, put brackets around it, use my subscript ij so that you understand I'm talking about the entry in this matrix in the ith row jth column. And I think if I'm going to discuss it, then I think I end up with nothing more than the following. W the sum as I misspoke, as k ranges from 1 to n of my a sub I, help me with this, guys.
Can I ask a question first?
Yes,
We didn't specify the dimensions of these matrices.
I know. So the first one's an n by n, the next one's an n by p, and this one may be a q by, no, this is my words. Let's suppose this is n by n, and this is an n by q. Let's suppose this was a,
N by Q. N by Q.
good, I agree. No other subscripts, it's still going to be n by q because I need to have these two matrices in the same dimension for me to be able to have them together. That was my point. So a sub, am I losing it? Is it j? I think it's a k. Times b sub kj plus kj. Do you guys agree? It's just that when you look at this matrix right here, what could you say about this matrix? What's its dimension? I'm just shaking you guys up, make sure we all understand where we're at. What's the dimension of this matrix?
N by N.
I was hoping you'd say, it's nothing, it's not a matrix. What is it?
It's a point in an element of a matrix.
A scalar, which means a real number. It's just a real number. Shoot, do we have a distributive property for multiplication of addition in a real number system?
Yes.
Of course
Yes.
we do. And so I think this is nothing more than the sum, as k plays this game, of a sub I k times b sub kj plus my a sub I k times c sub kj. Oh, but shoot, you guys knew from back in Math 30 that sums of sums are sums of sums.
Yes.
My summation distributes of addition. I think what I have sitting in front of me is nothing more than the sum as k plays this game of this product plus the sum of this product as k plays this game. But this is merely, jeepers, how can I put this? This is merely going to be this product matrix plus this one. I'm using my letters. Is it AC? Looking at the entry in the ith row jth column. Now, did you guys notice how I'm proving this particular statement, mathematically speaking? I really have my entire argument just talking about one entry, an arbitrary entry, in the arbitrary ith row jth column. Do you see my point? Daniel?
Yeah.
You guys made the question, I mean, what's most important? I think that's a big deal. I'd like to be able to submit that. You guys, before I go on, anybody else?
So
Yes.
technically with this, if you were to set B and C to different dimensions, you could prove that that does not work?
True, and I think that was Chris's point. I mean,
Yeah.
I'm making the assumption that all the operations of multiplication and addition were defined to prove this. And maybe I
Okay.
should have said that in English first. I just assumed that.
So it's kind of sketchy whether or not it actually works or not. It just depends on what you assign to B and C.
See, I disagree. I think if somebody asks you to prove the statement's true,
Yeah,
we're assuming all the operations are defined.
okay.
You might want to make up different letters than I did, but who cares what you call the letters? numbers.
Okay, so if somebody asked you to prove that it was false, you would
But
set
it's not
those-
false.
But it
It's-
could be.
But I think it's true whenever those operations are defined.
Yeah.
It's sort of like saying to a math B student, let's evaluate the function of 2. We would never do that because 2 is not in the domain of the function. It's not in our universe of discourse. I would never ask a student that question in math D. Just like I would never ask you in math 33, which is, we call it DE because it's just math D extended. We would never ask a person that's not true. Is anybody else? And then on the homework? Okay. All right. If not, can I get rid of this?
Sure.
You know, something I'd really like to do today. Something we're done already? I would like to talk about rewriting whole systems of equations. For example, if I had an equation a11x1 plus a12x2 all the way up to a1, I don't know, what do you think? What do you think I would say next?
X or A1N
Times x sub
and or
n.
X.
If this is equal to b sub 1. Then I had another equation, where I got a coefficient, I'll call this, I'm on the second row, how about down a sub 2, 1, x1, plus a sub 2, 2, x2, all the way down to maybe, how about an a sub 2n, x sub n being equal to b sub 2? That's fine. All the way down to my very last line, how about a sub, how about m1, x sub 1, plus a sub m2, x sub 2, hold up, I missed my dots. All the way down to the last term, which is a sub mn, x sub n being equal to b sub m. I think that's a set of m equations in n unknowns. And I think it's sometimes cumbersome to write. So if you guys don't mind, I'm going to change my notation. I'm going to take the collection of these m equations and replace it with a single matrix equation. I maintain that if A is equal to the coefficient matrix, and if I have a matrix X, you know what? It's going to be a column vector. It'll be a one-dimensional matrix. So can I change the notation? Can I use lowercase x and I'll just put a bar over it? I typically do that when I got vectors. And let's let x bar be equal to, I don't know, x1, x2, all the way down to x sub n. And finally, let b bar be equal to this column vector, b1, b2, down to b sub m, not n. Then I think my original system of m equations and n unknowns can be expressed as the following. You guys, this is kind of really slick. I think it'd be expressed as following single matrix equation. Namely, that if I take my A coefficient matrix, multiply by my x bar column vector, I think I'm going to get the b bar column vector right back. You think about it, watch. Pick this up off the board. Put it right here. Multiply 8x bar. When you look at these dot products, I simply get what you see on the left-hand side of the equal signs. But that would be equal to my b bar on the right-hand side of the equal sign, equating components by components. I regenerate those individual equations right back, all n of them. So I just think this is a nifty way to rewrite my original system as a single matrix equation. You guys aren't going to see this in the book yet. Can I show you where I go with this soon? Your book doesn't. Your author just kind of says this, hand waves at it, oh, we'll come back to it later. But what's really cool about having the single matrix equation is I can do something like this. Just like back in Math D, I can divide both sides by A. Shoot, you know what? I can't. There's no such thing as division of matrices. I have an alternative. I will simply multiply both sides of my equation by something I'll call the inverse of matrix A. We have associativity working for us when it comes to multiplication of matrices. And by the way, any matrix A times its inverse on either side is going to give me the appropriate size identity matrix right back. But haven't I already proven in class, last time you and I met, yesterday, right, that identity matrix times any other matrix is just itself? Oh, jeepers, nobody jumped. That means I got a way of solving for x bar, which means I got a way of solving for all the x values, all my n unknowns, just by looking at the inverse of the original matrix, multiplying by b bar. That's pretty slick. Well, that's pretty slick for us algebra people, Math D people. It's even more slick when I put functions in there. Which we will. Yes, sir.
In that example, I'm assuming the b is to the -1. Or is it just-
Michael, no, I'm being too sloppy. I meant it to be a b bar. I apologize. I tend to use this notation, lowercase letter with a bar over it, if it's a one-dimensional matrix. And over here, that's what I really meant, Michael, in the middle board. I'm sorry if I'm writing too fast. Chris?
It's really just a fancy way of saying that originally we had our inputs and we applied a linear transformation to get our outputs with our b's.
Okay,
And so we undo the operation of the b's and get our inputs again.
no, that was perfect.
Oh, it is?
He's saying this. He's saying multiplying x bar by matrix is applying some kind of function, or how about a linear transformation to the x bar. And to find out what the x bar is, we'll apply the inverse transformation to both sides, which is exactly what's going on. But that's not going to come for quite a few more chapters. So just maybe 3 chapters there. But yeah, I agree completely. Multiplying by matrices is a linear transformation. I'll prove that to you. So, can I come in here? Let me come back. If this system of equations has solutions, I sometimes say the system is consistent. If the system doesn't have any solutions, I sometimes will subclassify the system as being inconsistent. Just a bit of vocabulary. I will not be testing you on that. You won't see such a question on the exam. But if you see my word being used somewhere along the way, I expect you to know what it means. What if I had just said 2 equations? These are both linear equations. Do you think that system always has solutions? Do you think that solution always has systems? All right, don't answer my question. To solve the system means what geometrically, not algebraically?
Point of intersection.
To see if I have an intersection between two
Blade.
lines. Well, just lines. I'm just in 2 space. So question, take 2 lines in 2-dimensional space. Do you always have a solution? No, they could be
Parallel.
which means the system is
Inconsistent.
you don't want to play. Inconsistent. I agree. We could also say that the 2 lines intersect at a single point, and there you get how many solutions?
Just one.
1. Or you can say the lines are on top of each other, meaning you have how many solutions?
Infinite.
Infinitely many. So I think when it comes to lines, there's only 3 possibilities. We have 0 solutions, exactly 1 solution, or infinitely many solutions. Meaning the lines do not intersect, they're parallel, or they intersect at a point, or they're coincident, they're on top of each other, respectively. What about this system?
Do the same rules work for planes as well?
Oh, you beat me to it.
So
For those of you who have not graduated from Math 32, you might not recognize this as being a collection of three planes, but they aren't. They're not lines in three space. Now, three planes, do you think the same thing holds if they have either zero solutions, exactly one, or infinitely many?
Yes.
Yeah, I agree. Have zero solutions if they all are
Parallel.
parallel, or maybe just two are parallel and one cuts through like that. The all three don't have something in common.
Yeah.
You can have exactly one solution by here's one plane, here's another, and here's another. They seem to intersect exactly one point. Or you can have infinitely many points, like geometrically, that would be what would it look like as an intersection if there were infinitely many solutions?
They're all overlapping at the same place.
That's one way to do it. All three planes are the same. You have infinitely many solutions, an entire plane. But it might just be a line. Maybe here's one plane, here's another, and the other slices in at that line of intersection. So having infinitely many solutions may mean you either have a plane or a line. We'll have a neat way of talking about this in the near future with vector spaces, but at least you can visualize that, and I'm happy. Alex?
I'm a little curious. I'm looking at these matrices, and I'm seeing the x how it 1, 2, and 3. Okay. It seems like it would be multiplied in as a row instead of a column. But
You know what, you guys, let's see if he's right. Do you think I can take this x bar and just put it right over here real quick? And the b bar is the same size, isn't it?
Right.
Everybody?
Yes.
Yes.
Say it again? I can't hear you.
No?
No.
Okay.
It's got an M I as opposed to N. Let's see if this is really true. Do you mind? Well, I think here I've got an n by n, but here I got a n by 1. I want a yes or no answer. Is multiplication defined?
Yeah.
I think it is. Because I think the number of columns the first is the same as the number of rows the second. And I think the resulting product matrix will be of dimension n by 1. That is to say, the number of rows of the first by the number of columns of the second. Oh, but wait a minute. On the right-hand side, clearly this is of size m by 1. Oh, good, thank goodness. I still might have made a mistake, Alex, but at least these two matrices in the end have the same dimensions, and so equality could hold, but it's only going to hold if corresponding entries are the same. Let's see if they are. If this product is n by 1, then let me try to draw an n by 1. Here it is. Here is the item in the first position, second, all the way down to the nth position. Let's see what these items are. In my product matrix, this entry is in the first row, first column. So I guess I better dot the first row, the first, with the single column, the second. But that dot product ends up being this. Oh, by the way, I missed something. On the other side of the equal sign, I guess this n by 1 matrix, I can rewrite this line. So do you guys think that these two entries really are equal to each other?
Yeah.
Of course they are. It was my very first equation. Do you think I could stop writing? Say, Alex, I think each of the corresponding entries are equal to each other because they're the original equations I created. I'm just shaking it by suggesting that if I really want to, I could rewrite the entire system in this flamboyant fashion because I think it's sophisticated, and maybe the tools of matrices will help me solve these equations much more easily. Actually, and that's all just one brief second, because I'm going to use this.
So I'm a little confused. If we're saying that the X column matrix and the B column matrix are not equal to each other, then how come it looks like they are over there?
Can you say that all over again? I didn't just
So when you said earlier, you asked us if those two columns were equal to one another, aren't they?
only
Or
are they
in the
not
same
equal to each
length
other,
or
they're
in the
not
same
even-
dimensions?
They're not even the same dimension.
But
and
if our nth dimension there is equal to B sub m,
Uh-huh.
aren't we saying that B sub m is right there where the nth dimension is?
Here's what you're missing.
Or the mth dimension, sorry.
Here's what you're missing.
Okay,
This matrix is of this size.
yeah.
this matrix of this size. After I multiply them together, I'll get a whole new product matrix which is of this size. And that's what I have down here. That n gets absorbed in the dot product. Because that's what my k is going to do is range from 1 to n, so you only see the number of rows of the first matrix by the number of columns of the second matrix.
Okay.
Because we're skipping over quite a few, you get the assumption that n and
Oh, yeah.
m are equal.
I know. It's tempting to say even what Brad was saying. Well, look, column vector, how can they have a different size? Because through the multiplication process, that dimension gets absorbed in the product matrix. What about this? What about doing something slightly different? Just talking to you guys, I'm just talking very lightly about notation, and I promise today in class, I'll get down to solving some systems. I'll be sophisticated. Just another brief moment. What if I told you this? That the derivative of x of 1 with respect to t was equal to, I don't know, how about an a sub 1, 1 times x of 1 plus an a sub 1, 2, x of 2 plus, how about a b sub 1? Suppose I had another differential equation, d sub x2, derivative of x of 2 with respect to time t is equal to a sub 1, 1, hold it, everybody. Can you just appreciate that I really am thinking of x1 and x2 as functions of time t? That's what I'm really suggesting. And maybe this is equal to different coefficients. How about a sub 2, 1, x1 plus a sub 2, 2, x2 plus a b sub 2? I think those are two differential equations. And I think I can rewrite this entire system in the following fashion. I think I got my x bar prime of t being equal to my a times x bar t. I can rewrite that system of differential equations using exactly the same logic as a single matrix equation. And again, here too, we will. And we'll use our tools of matrices to actually solve that system of DEs.
Can you show us like an example of that? Or is that kind of beyond where we're at right now?
I can show you whatever you ask.
Okay.
I got a population of wolves. And I've got this population, they're all alone. They have nothing to eat. Are they happy?
No.
No, so I think the rate at which the population changes over time is going to be proportional to how many wolves I have at any given time. Can I treat all the constants I put on the board for this brief moment, treat them all as constants that are positive? Don't you think I should have a negative sign up front? They have nothing to prey, and therefore their population is going to be decimated. Suppose, however, I have a population of rabbits, and there are no wolves around. I think that population is going to be happy. Can I call it K1? I'll call it K2.
Well, do they have food?
Yeah, they're rabbits. They're just eating the grass.
Okay.
They're fine. All of a sudden, of course, I put these two
Unless they're in
populations
the
together.
desert.
And I think if I put these two populations together,
Unless they're in the
what's
desert.
going to happen is that for the wolves, their interaction is a positive experience for the population. Gosh, how am I going to quantify that? It's this easy. I think the benefit for the wolf population is going to be proportional to the number of encounters. And I think the number of encounters itself is going to be proportional to the product of how many wolves and rabbits I have. So Bradley, I'll modify my mathematical system by adding to the rate at which a wolf's population is changing over time some other constant K3 times R times W, so that I'm mathematically including a positive interaction that's proportional to the number of encounters between the two species. I'll play the same game with the rabbits, it's just that they're not going to be very happy about it. I'm going to subtract off, aren't I? And I just try, Brad, to answer your question in 60 seconds. I just try to find a natural way of building a system of differential equations, for which I may be able to rewrite that way. Now, there's something wrong with what I'm writing, though, technically speaking. Here are my rabbits, there are my wolves. You notice how x1 and x2 are all by themselves in these terms. I do think this system's a bit more complex than what I have over there, only because I've got the product of those populations, and that is cumbersome. But sometimes we can modify that.
I was just gonna ask, is there a way to manipulate that so that you can separate your variables?
Sometimes there is, sometimes there is. Sometimes I just can't avoid it. And sometimes when I can't avoid it, like, sometimes when I can't avoid it, I just give up. And I just draw a picture, and I talk about the interactions in those populations, sort of like a skill field. Or maybe I won't solve the actual system because it's so complex, but I can talk about trajectories in terms of how the populations are interacting. And I can answer the question visually as opposed to analytically. Gosh, I forgot where I was at. Do this for me. Let's start looking at examples. I know this is a Math B question, but humor me for a minute.
Solve it using a matrices, substitution, addition.
How about something completely new?
Okay.
I want you to solve this system not using your traditional Math B techniques, but creating an augmented matrix and reducing the matrix. So let me tell you what I mean by using all those words.
Y would be a x2, basically.
Yeah, y is acting as my x2 and x is acting my x1.
Yeah.
I just think that if you guys, if we're going to solve the system using Math D skills, I'm wasting a lot of ink. Because I think x is just a placeholder, y is just a placeholder, so I'm going to use a matrix as a placeholder. I will go ahead and create a matrix and list the coefficients of my first equation, list the coefficients of my second equation, put that in my second row. Now personally, if this matrix represents a system of equations, I have a tendency myself to put a vertical bar here just so I know where the equal signs are. Now would you guys not agree that if I were to massage this matrix and put it in this form right here, would that be beneficial?
No.
No.
Because that's just nonsensical.
Oh, I know, but I'm making up. I'm saying
Okay.
I don't want to do the arithmetic yet, but this is a number, that's a number, that's a number. Do you think if I could massage this matrix to look like that, would that be beneficial?
Yes.
Why? Why?
Because you have it's if you're subtract or using addition there or Gaussian elimination.
I've never heard of those words.
Okay.
Why would this be beneficial?
Because it's easy to solve.
Because if you rewrite back in equation form,
Yeah.
this tells me y is equal to that number.
Yeah.
And I can back substitute in this equation.
Yeah.
Find x. That'd be beneficial. And sometimes when I transform a matrix in this form, where listen to my choice of words, where all the zero rows, all the rows with nothing but zeros are at the bottom, and every first entry in a row is going to be a 1, and any leading one you see in a row is to the right of the leading one above it, unless of course the first row. Then I will say my matrix is in, anybody know? Echelon form. However, if I were to massage this matrix even further, not the same pound symbol, not the same percent symbol, wouldn't that be really cool? All you have to do is just glance at it and say x is equal to that number, y is equal to this number. And so whenever my matrix is in echelon form, and if I've also got these columns involving these leading ones with zeros everywhere else in those columns, I might even add to the flavor. I might say it's a reduced row echelon form. So row echelon form, reduced row echelon form. The process of transforming this matrix into row echelon form is what I sometimes refer to as Gaussian elimination. But to massage a matrix and put it in reduced row echelon form, I might say I've used Gauss-Jordan elimination. Now I have to confess, I have not given you steps in the procedure of getting from here to here or here to here, but there are specific steps and there's only 3 of them.
What is the difference between Gauss-Jordan and Gaussian? I thought they were the same thing.
Dramatically not. I think
Okay.
if you're going to use Gaussian illumination on a matrix, you're transforming the original matrix into one that is in row echelon form.
Okay.
But Gauss-Jordan illumination is taking it a step further and putting a reduced row echelon form. The idea
Okay.
behind reduced row echelon form is this. What you see to the left of this bar is unique. But with row echelon form, it's not unique. So you might have many different versions. And if I
Okay.
ask you to solve a system with augmented matrices using Gaussian illumination, that means when I go home, I got a headache. All your answers are going to be different.
Okay.
Well, the matrices will be different. The final solutions will be the same.
The reason why I asked the question I asked earlier is because at least from my understanding, when you apply Gaussian illumination to a linear system, you're relying on the fact that that system has particular properties unique to linear equations.
Yes. And you know what? I have to confess, I'm assuming these are linear equations.
Okay.
I'm assuming that.
Which is why I asked, if you have a sine x and there's a transcendental function or something really crazy, can you really use Gaussian illumination?
So I think there's something you're not seeing. I think this system equation, I could interpret as being a linear system in terms of my y's. It's just my coefficients are really what the functions are going to be. When I was talking about functions and the positions of these matrices, I was really referring to the coefficient matrix as having these functions. So I think I could solve the system in the same way I'm over there because it's a linear system when I put the special glasses on, system in terms of the y's. Even though the coefficients themselves are functions in x, that's fine. I can still solve the system with the
So
usual match.
you would say that the system that you have up there is linear with respect to the y variable because doubling the
Yes.
input doubles the output, and you can take the system in parts.
Yes, I can take the system parts like I did before with my single matrix equation. And besides that, all the y's you see are just being raised to the first power. They're not being multiplied or divided to each other. It's just my coefficient matrix is really what's a non-constant coefficient matrix. That involves a function.
I was just uncomfortable because of that.
And I wasn't, you're asking again because I think it was very unclear in answering your question. That's really what I meant.
Right.
So everybody, let's give it a shot. Here are my 3 tools that I'm going to be using in reducing a matrix. Can I put them over there? They're so important, I'll give them a name. I'll call them my elementary row operations. Everybody, I do not have a long list for you. It's a very short list. There are only 3 elementary operations, and they're all very, very easy. It's just repeating yet again what the heck you and I did back in Math D. So here I go. I think, if I can find a decent black pen, I think, in a matrix, I can permute any 2 rows. Guys, I am really tired again. I don't like what I just said in English. I said in a matrix, I can permute any 2 rows. I didn't mean that. I meant, if I got an augmented matrix representing a system of linear equations, I can permute any 2 rows. That's what I really meant. Now, the reason why this is legal is because check out this very first row. It's just representing that equation. The second row represents this equation. And in permuting any 2 rows, it just simply means I'm listing the equations in a different order. That's not going to affect the solution.